Okay. Well, hello everybody. It's really excited to begin to get involved with Topos. So, and I'm very happy to meet everybody. And I thought it would a nice way to maybe begin to get to know some of you and vice versa would be to share some of the ways I've been thinking coming back to category theory and using some very basic stuff to organize some ideas. So that's what this rather experimental talk is about. Okay, let me. Oh, okay. Well, the abstract is up on the website, but just maybe to give a quick overview of what is going on here. What I'm going to talk about is the intersection of a couple of different things that I'm interested in: categories from a very long time ago, and markets, mainly financial markets, which is my field today. Physics, which I never really got to study properly as an undergraduate, and which I would like to learn more about one day. And ancient Egypt, which is a more recent interest. So what do I mean by the goal of this is to try and figure out a way to model and understand and simulate decentralized markets. But what do I mean by centralized versus decentralized? So here's the kind of archetypical example of a centralized market, which is the equity market or the stock market. So, or more precisely, a single stock exchange. And so you can see here, you go to the New York Stock Exchange, and there's a whole bunch of stocks listed, and you can buy and sell them in terms of dollars. And it's the fact that there's a single special asset called dollars that's the basis of all transactions that makes this a centralized market. And in finance, there's a very standard kind of undergraduate way to model centralized markets, which I'll call the classical model, though no one really calls it that because it's taken for granted, which is there's a single unit of account, dollars, let's say, and at each instant, every asset has a price in terms of dollars, and that price vector follows some form of n-dimensional Brownian motion, or sometimes people generalize that, but that's the basic idea. And the different assets, they'll have different volatilities, different correlations, and so those characteristics are all bundled up in a covariance matrix. And there's different ways to formulate that, but for reasons I'll explain later, I think one nice way of thinking about it is in terms of path integrals, that you can, given any particular path, some realization of the vector of asset prices over time, there's an action on functional list defined on that, which defines its probability density, and that gives you a measure on the space of paths, which turns out to be basically Wiener measure that describes Brownian motion. And this whole path integral approach to finance goes back more than 30 years and has been used. It's always been a bit of a fringe thing, but it's been used for practical applications for pricing path-dependent options and stuff like that. Okay, well, so what are some examples of decentralized markets? And by decentralized, all I mean is that instead of transactions occurring in terms of a single unit of currency or a single measure of value, there are simply exchanges between different assets. So these can be barter markets. The first markets were like this. The papyrus on the right-hand side, or the left-hand side, was written by a scribe, a Middle Kingdom Egyptian scribe called Hekanukt. And he's describing how there's a bunch of people who owe him grain, and he's willing to take a jar of oil. This is the left-hand column. He's willing to take a jar of oil in exchange for 2 sacks of barley, or in exchange for 3 sacks of emmer wheat. A more modern example, a currency market. So when you trade currencies with an FX dealer, then you don't translate everything into a central currency. You can just trade a currency pair. You can trade sterling versus Japanese yen without having to go through dollars first. And then a more recent example are cryptocurrency exchanges, where you don't have to go through dollars or through Bitcoin or Ethereum. A typical exchange will let you trade directly between different pairs, although not every pair is tradable on every exchange, obviously. Now, an interesting thing about decentralized markets is there's generally or very often the possibility of arbitrage, and that you can exchange two assets maybe in different ways through different sequences of exchanges, and you don't necessarily end up in the same place. And sometimes you can even go around in a circle and not end up in the same place, but make essentially a riskless profit. In FX markets, that's generally really, really small and probably persists for fractions of a second. But in markets like crypto and especially barter markets, larger. Now, I gave the stock market as an example of a centralized market, but actually, that is not quite accurate to think of it like that, because it turns out that equities trade on different venues, and there can be arbitrage between different venues, and maybe even for the equity market, a more decentralized model is a more useful way of thinking about that situation. And these arbitrages aren't trivial. They can persist for hundreds of milliseconds, which is a really long time, and businesses built around them. And there's actually quite a nice book called Flash Boys about this whole situation by Michael Lewis. There've been a number of previous efforts to analyze decentralized market structure. So there's a recent paper on cryptocurrency arbitrage, which uses kind of graph theory to look at arbitrage across different crypto exchanges. And going back a lot further, there've also been previous efforts, starting with Alinsky about 20 years ago, to model arbitrage in markets, basically defining markets in terms of possible exchanges, or a lattice of different assets, that you add a time dimension to the lattice. You define prices of the assets as sections of a simple bundle over that lattice. So a state of the market is some connection, and arbitrage exists if that connection has non-zero curvature. So what I made a start or a stab at doing here is thinking about, well, what might be an interesting categorical theory of decentralized markets, and what should that theory be able to do, and hopefully it can do some interesting things. It can incorporate the classical theories as special case. It can help you understand how shocks lead to arbitrage and how arbitrage dissipates over time. Maybe you can talk about convergence to fair value as well. And maybe you can ask questions about what it means to merge markets together. What happens if you can trade across crypto exchanges or across equity venues? Okay, so in a nutshell, what does this look like? And really, there's really nothing going on here, except almost no category theories as an organizing principle. So what's a market? Well, a market's defined by a weighted directed multigraph. I'll explain in a second what the weights mean. And the edges in the multigraph of possible exchanges of assets. You formed a free weighted category which corresponds to sequences of exchanges, and then a state of the market is just a functor from that into the additive reals considered as a category through its monoid structure, which intuitively takes an exchange to the exchange ratio of those assets. Now, you have to be a bit careful about what you mean here, so I'll come back to that on the next slide. Then a path is just a sequence of states. Assume you specify some time steps. You can define some Lagrangian on paths with some terms that are going to make this look a bit like the Wiener measure, but also penalize arbitrage at particular states, and then define the probability of density of a path in the usual way. So what's the interpretation here, just in a bit more detail? The objects of this directed multigraph M are a set of assets. And we assume that all the assets are fungible and infinitely divisible assets. So this is not like a model of OpenSea or something. So an edge corresponds to an offer to provide asset B in exchange for asset A. So B posts an offer, then the owner of asset A decides whether to lift the offer. And the mass of an edge represents how much that the exchange ratio between A and B resists change, how sticky that exchange ratio is. And composites are just sequences of exchanges. And a state, which is this functor from the free category M to the additive reals, that when the market state is X, the arrow F, X of F means that B is offering to exchange X of F units of asset B for asset A, which A can choose to lift if they want to. And there's a technical note, which I think you should just ignore right then. Okay, and then on top of this, you can layer some additional definitions that help you relate this to other concepts that we're familiar with. So traditionally, a numeraire is some asset that can serve as an accounting measure. Dollars are the commonest one, but you could use sacks of grain or ounces of silver or a particular cryptocurrency. And so formally, you can define a numeraire to be a spanning star. And you can say that that's actually a medium of exchange if you've got two-way arrows in the star instead of just one-way outward arrows. And we could call a market weakly centralized if there's a medium of exchange. And if these two-way arrows are actually mutually inverse, then you could say that this was a perfect medium of exchange. Any two such are isomorphic. So, but that doesn't mean that their exchange ratio is static. That could fluctuate. And importantly, perfect media of exchange actually don't exist in the real world. So this very idealized situation. You can talk about shocks and think about how they propagate, although we don't have that machinery yet. So a shock in general to a state is just another state to which it's perturbed. But given an asset, a particular asset, then you can define what it means to have special types of shocks. A supply shock to an asset affects all the arrows with codomain A, and a demand shock to that asset would affect all the arrows, possible exchanges with domain A. So the classical model can't distinguish between supply and demand shocks. They're the same thing. So I think that's one of the nice features of a model like this, if you can get it to work. So for example, that's got a natural interpretation in the case your asset is a numeraire like fiat money, where a demand shock means that owners of other assets are willing to offer them at lower prices. And a supply shock means that owners of the numeraire are willing to bid high for other assets. For example, you've got the money supply has been expanded. There's also some useful definitions as well. Here's a simple one, which is if you've got two markets which share the same assets, the same objects, like two different equity trading venues, then it's straightforward to define their merger of those markets as push out, and you can compare the behavior of the two markets to the single merged market. And also, you can talk about what it would mean to have a market with refunds. So for every arrow there's some distinguished way of going the other way around. You don't assume that they're inverses, but just that you can always reverse a transaction, and that can give you some interesting additional structure to look at as well. Okay, so that's the category theory part, and there's really not very much of it. So what about the physics part, or like the quote physics part? It's not really physics, right? But it's just some terms that you throw in there to define an action that are kind of inspired by physics. So what kind of terms should you have in there? Well, firstly, there should be something that makes asset prices behave like Brownian motion. And so that's got to be a term that looks a bit like kinetic energy. And it's going to depend on the mass as well. The second thing is you want a term in there that makes states where there's lots of arbitrage less probable, and helps drive on in expectation paths to evolve in a way that reduces arbitrage. So I think the way to think about that is arbitrage as a form of potential energy. Looks a bit like elastic potential energy, and it should be defined for parallel pairs, which in the absence of arbitrage should give you the same exchange ratio, and also for loops, going around in a loop should be the same as doing nothing if there's no arbitrage. And finally, if you've got some notion of fair value, for example, if you think, at fair value, 2 sacks of emmer wheat have the same nutritional value as a sack of barley, then market prices, market exchange ratios can deviate from that, but maybe you want some sense that things over the long run tend towards their fundamental value. And so that's another potential energy term, which is a little bit more like gravitational potential. So what do these terms actually look like in practice? They look kind of like what you would expect them to look like, but there's a little bit of a kind of little twist here, which is in the kinetic energy term, the m is in the numerator. So the higher the mass of an arrow, the more resistant the exchange ratio is to change, and so you're penalizing bigger changes. But in these arbitrage potential energy terms, the mass is in the denominator. So the idea is that the lighter an exchange is, the easier it is for change, then the more likely it is that arbitrage gets eliminated. And so the more you penalize states where arbitrage is high. Anyway, aside from that little wrinkle, there's, I think, nothing all that surprising about the form of these terms in the Lagrangian. Oh, but I should mention, so in the potential energy term down here, this idea of you penalize states which are distant from fair value, you have to come up with what a coherent notion of fair value actually is. So this fair value state, the right-hand term, can't be just any old state, I don't think. And a coherent notion, I think, turns out to be a state which is arbitrage free. And that simply means that it's going to factor through the quotient directed graph of this free category. And it's pretty easy to see that if a state is arbitrage free in that sense, then the transition from that state just to itself has a zero Lagrangian, and the path where asset prices just remain at that state forever is, I think, fairly trivially the path in the in-path space with the highest density. Except you don't necessarily start there, so your dynamics can be interesting if you start somewhere else. Okay, so let's take a look at what some simulations look like then, if we set it up that way. So, and for reasons I'll explain in a second, I've only said.
Oh, Wesley?
Yeah.
Can I get you to define quotient directed graph for me?
Oh, yeah. Okay. So if if M is a category, then that quotient graph is going to be the biggest directed graph that M maps to, in the sense that if M maps to any map from M to another graph will factor through M tilde. And what it really looks like is simply M tilde is a graph where there is an arrow from there is a unique arrow from A to B in M tilde if there's any arrow or maybe many arrows from A to B in M. So it really just identifies all the arrows that go from one object to another. It's a pretty simple object. Okay. And that's what forces it to be states on it to be arbitrage free.
Right, that makes sense. Thanks.
Okay. So simple example, and you're only going to get simple examples, unfortunately. A commutative square, where let's assume that you just got unit mass for all these arrows. So what does that look like? Well, GF and KH are both ways of swapping asset D for asset A. So in the absence of arbitrage, they should have the same exchange ratio. So when you run simulations, what does that actually look like here? Well, if you look at some scatter plots, the relationship between changes in F and changes in H, the two arrows pointing out of A, not much of a correlation there. But if you look at changes in the composites GF and KH, which are parallel pairs, that's parallel pair from A to D, then those are the red dots there on the left. And there, you can see they're very highly correlated because of this term that penalizes arbitrage in parallel pairs. And on the right, you can see that if you look at the distribution of the differences, quite loose for the change in F and the change in H, but not for changes in the composites, which both have to change in the same way at the same time almost. Okay, so this is pretty intuitive, but it's just good to verify that you get what you expect to get. So how efficient? I said we're just sampling a lot of different paths. They're really simple paths because there's only one time step, and then working out the weight by calculating the Lagrangian. How efficient is sampling actually? And this question is going to come up in a very serious way when we simulate multiple time steps. And the answer is, well, not super efficient actually. So here's a couple of charts where each dot is a random draw, and I plotted the y-axis is the weight, and on the left the x-axis is kinetic energy, and the right is arbitrage potential. And the first thing you see here is that there's just a lot of draws with weight 0. So you're or essentially 0. So you're drawing a ton of samples which you're essentially throwing away. So that's kind of annoying. And also there are just parts of this space which are not particularly well covered. So ideally you would like to see on the right-hand chart maybe more dots on the left-hand side with very low arbitrage potential, high weight shifts. Okay, well, what about an opposite pair? So if you've got arrows from A to B and from B to A, then if you just ran the simulation on this directed graph, then there would be no constraint that going in a circle should have low arbitrage. It's only when you move to the free category and look at composites which is the same in the previous example, that those arbitrage potential terms really bite. But the question here is, well, how how much do you need to expand the free category in order to get good simulation results? Is it fine to look at paths of length 2, or do you really need to be able to loop around twice, look at paths of length 4? And this comes up obviously for more complicated graphs as well. And the answer is, well, if you only look at paths of length 2, then even just cutting off the expansion at that point, you're still kind of enforcing that there's not very much arbitrage. But you do seem to sample differently in terms of weights if you take more paths in the expansion. So there's some sense it does make some kind of difference somehow, although I'm not absolutely sure how, to be honest. Okay, so I dwelt on that a bit because it turns out that when you try and sample multiple periods, like instead of just one period, maybe 12 months or 60 months or 100 seconds or something, then you run into some pretty severe problems where I only have tentative solutions right now. So what you want to do is sample random paths, and then you know how to calculate the weight of a path by computing the action. But what you want to do is sample mostly from the region of path space where the density is, which in other contexts, like probabilistic model, is called typical set. And the problem here is that especially when there's a situation where you can have arbitrage, the typical set is a tiny part of path space with a very weird shape. And so when you're sampling naively, you often just never end up sampling anything from the typical set. It's a vague definition, but you see what I mean. Even though that's where the density is, you just miss it entirely. And instead, you sample a couple paths which happen to have lower arbitrage than the others, and then all the others have weights that are orders of magnitude less than those, and then you've got a very high weight to just a handful of paths. I'll show you a chart in a second. So that's classic. That problem in the Monte Carlo literature is called weight degeneracy, and it's an annoying problem. So one way to solve that actually is to be smarter about how you sample. So if you sample a path, you're sampling one time step at a time, at delta f at time 1 and another delta f at time 2 and so on. And one way you can mitigate this problem is, as well as shocking each arrow some more in each time step, you can also impose some closure of arbitrage at each time step as well. So include some dissipation adjustment at each time step, as well as an additional shock. And if you pick something that's like a reasonable approximation to that true dynamics of how arbitrage closes, then you're basically carrying out some kind of important sampling here, and you can hope to sample more from closer to the typical set. And in fact, that, like in the very simple small examples, that actually does work reasonably well. And so that's what the following example is based on. But even then, it's not great. So here's an example with no arbitrage possible, just to give you a sense of what things look like, and sampling is not problematic. So let's say you've just got a single arrow, 2 assets and a single arrow. And what does sampling look like? Well, the simulated path looks a whole lot like Brownian motion, and you can see that the bigger the mass of F, in the sense of weighted categories, then the less the paths can move around, the more the tighter the range. So that's what you would expect, and that's what you see. That's kind of good. Okay, what if, and again, no arbitrage possible, what if you impose some reversion to fair value? Let's say you say 0 is fair value, that a 1-for-1 exchange of asset A to asset B is fair value. Then if you add that fundamental fair value term to the Lagrangian, then you get the yellow paths, and you can see there that they're still random, but they're attracted back to zero, and so they don't spread out over time. So again, that's what you see. Okay, so let's add the possibility. Oh, and if you start out away from fair value, then you move around kind of Brownianly, but you also drift back to fair value. That's what you want to see. Okay, so what happens when arbitrage is possible? So simplest example is two parallel arrows. And so what you can see here on the left, a bunch of simulated paths for F and G. You can see they can move around a lot, but the most likely paths are where they kind of track each other. And the difference between F and G moves around on a much narrower range. That's the thing that's controlled by this penalty on arbitrage. So this is nice because it's what you we can already start to see a problem on the left-hand side because it's just really a few paths have disproportionately high weight. If you, in addition, add reversion to fair value, then you move around less on the left-hand side and you're similarly constrained on the right by low arbitrage. And if you start out with some shock to one arrow or versus the other, F is a very different exchange ratio from G, then what you see is that they move towards each other as arbitrage dissipates on average, and also they both move towards fair value. But you can already see here there's a big problem with weight degeneracy. I simulated 10,000 paths here, but only one of them has enough weight to even show up on the left-hand chart. Okay, and then just if you have an opposite pair here, then the dynamics of the two are limited by arbitrage. So you kind of see what you expect here, but again, you have a problem with weight degeneracy, which I've illustrated here. This is a scatter plot of the terminal values of the terminal states of F and G and the weight by path. And you can see actually there's only two paths which really get any weight that's not negligible at all. Okay, let's go back to just the single period simulations where we can do a little bit more. And I just wanted to show you some graphs on the volatility and correlation structure that's implied by this, because you can get the sort of, I think, surprisingly rich structure from these really very simple categorical definitions. So single arrow from A to B. How volatile is that exchange ratio? How does that depend on the mass? The intuition is that the higher the mass is, then the lower the volatility is, and then this is indeed what you see down in the chart in the bottom. Okay, let's suppose you've got three assets. You can think of A as dollars if you want to, and you've got two exchanges that you're interested in, F and G, but also the assets B and C are linked to each other, right? So what do you expect here? You expect that because you can exchange B for C, so that there's two ways to get from A to C, then that's got to impose some kind of correlation between F and G. And it turns out that it does, and that the size of the correlation depends in a way that's kind of hard to guess on the mass of that link between B and C. So that's sort of interesting as well. And I'm not sure I have a really good intuition behind this yet, but this is just how it comes out. If you've got an opposite pair of arrows, if there's no arbitrage, then the exchange ratios are perfectly inverse. And so you can have arbitrage, and so they should just, the shocks to F and G should just be negatively correlated. And again, that's dependent on mass. That the lighter the arrows are, then the bigger the negative correlation, because the easier it is intuitively to close the arbitrage. And if you look at more complicated diagrams, here there's three ways of getting from A to D: GF, KH, and J. And if you do one period simulations using this diagram, unit mass for everything, then you actually get sort of quite an interesting looking and I think not really trivial correlation matrix between all the different arrows, including the two composites. Okay, so what next? Well, I guess the most serious problem is how hard it is to do multi-period simulation and avoid weight degeneracy. So I think that's the most important open issue in trying to do anything else really interesting with this, if that's even possible. And this kind of dissipation heuristic that I described there only seems to help kind of in very, very small toy examples. So, maybe another thing you should do is do it the other way around, actually draw arbitrage free paths first, and then introduce arbitrage into them in some kind of random way. And that's a better way to sample, and you can get draw more stuff from the typical set that way. So what you would do is actually not sample from the marker M at all to begin with, but from the quotient graph, and then lift that to M, and then add small arbitrages such that where the potential energy was a lot less than the kinetic energy of the path. And maybe for each arbitrage-free path, you sample a lot of paths with arbitrage around it, and that might be a good way to sample. So I haven't tried that yet, but I think that might be promising and helpful. Now, the other thing is, okay, let me go back here. This showed how the correlation of these arrows F and G varied depending on how strong a link there was between their codomains. But you can see you can't get a negative correlation here. And in general, the model as stated cannot model markets in full generality. You can't model negatively correlated assets. You can have negative correlation in arrows, but only because they're pointing in the opposite direction. And you can't really also model things like short positions and leverage positions. So in order to do that, it's a bit unpleasant. But you can do that in an ad hoc way by adding coupling terms to the Lagrange. So if you've got two arrows, F and G in this situation, if you want to force them to be negatively correlated, then you could add a new term to the Lagrangian that was proportional to the kind of difference between their shocks, and the constant that you add there is going to determine that relationship in expectation. And if you wanted to model, say, a short position or a leverage position, then you actually join a new asset and then do the same thing. So this turns out actually to work, unsurprisingly. So F and G, if you add sort of a coupling term, as I suggested, between F and G, where it's just where lambda equals, say, -1, then depending on, well, as you vary lambda, the correlation, you can get any correlation you want between -1 and 1, so that's good. But interestingly, there's some implications on what the volatilities can be. So there's something a bit delicate going on here. And the other thing, this bit's not surprising, is that the stronger you make the coupling strength, then the more extreme the correlation you get. Okay, so I just want to close, and I finished pretty early, but I think that's okay. By talking about what next. So the first thing is it's annoying to have to do everything through simulations, and it's hard. So it would be kind of nice to be able to describe the probabilistic evolution of asset prices, exchange ratios rather, in a different way. In a classical model, you know that in addition to that path and integral setup, you can describe the way you can describe Brownian motion and the evolution of prices under Brownian motion by a Fokker-Planck equation for the probability density function, how that evolves over time. It would be nice to have something like that here. And it's probable that that exists, I think. Calibrating to real market data is kind of important if you wanted to try and relate this to the world, actual markets. And right now, that doesn't seem to be very tractable, hard to do, because simulation is so hard. A useful thing to do would be to look at responses to shocks, like when I mentioned before, you can talk about supply shocks or demand shocks, or maybe other kinds of shocks. So it'd be good to formulate some notion of impulse response function to formalize how other parts of the state of the graph, the category change when you shift one part, like impose a supply shock on one particular asset. And in particular, what you would like to see is that shock should create arbitrage, and arbitrage should close over time. I mean, that happens in practice. You know that happens in practice. We see that, like in both the financial crisis and the COVID shock in March 2020. Even in normally quite liquid markets like stocks and bonds, you saw arbitrages open up for short periods of time and then close again. So it'd be nice to be able to model that using this framework. One thing that's missing from all of this is, but that's very important in the real world, is that you can borrow assets, you can lend them, you can hold on to them, and they have some intrinsic rate of return over time when they can differ from each other. And so it would be nice to figure out how to build that in as well, although that's probably going to be quite complicated. And finally, what does it mean to price options in this context? What does it mean to manage a portfolio of different assets when you don't necessarily have some central medium of fixed change? And I think you end up having to, especially for portfolio, so you probably need extra categorical structure, but I don't know what that looks like. Okay, well, I'll stop there. Thanks. You've been very patient with me because this is it's kind of flaky, but it was fun to play with.
Yeah, thanks. Maybe we'll have some questions. Yeah.
I have a question. Yeah, but it's maybe it's a little. So can you go back to the Lagrangian slide? I was just the very first introduction of energy.
Like slide
Yeah.
20.
Yeah. Let me go back there. Sorry. Yeah.
Yeah. So I had just a question on interpretation.
Yeah.
It looks like the potential here scales with radius squared. Like.
Yeah. Yeah.
So it doesn't look like one of ours. So not just the mass being inverted, like that interpretation is clear. What does it mean for this distance? Like, what's the interpretation on your potential growing as a function of radius?
Squared. Yeah. So this was so pretend that the mass is like the inverse mass for the reason I mentioned. The reason there's a squared term here is that this is the idea behind this is a bit like elastic potential energy, that having an arbitrage between two arrows is like stretching them apart when they really want to be together. And so the normal expression for elastic potential energy has this squared term in there. But I just made that up, and I mean, who knows what it really looks like. So it's actually, I think, if you could actually calibrate this to market data, then you could figure out, you can maybe get a better idea of what these terms should really look like.
Yeah, I'm realizing I was confused because you took gravitation form with like two masses, inverted it, but actually wanted the intuition from like spring potential, not gravitation potential.
Yeah, yeah.
Like, okay, cool. And then my other question was, so does this Lagrangian give us like, can you do Lagrangian mechanics? Like, can I get conservation of like energy if I take like a coordinate derivative?
Oh,
like,
I have no idea. Yeah, that's a good question.
Cool,
Yeah.
cool. Kind of cool. Thanks.
I have a much more stupid question on that one, because I kind of thought that Lagrangian was introduced to make some notion of fair value happen,
Yeah.
right? And then, you know, I actually, the stupid question is, we want to have a notion of fair value, and then you kind of pick up from your magician's hat the idea of Lagrangian, or you kind of knew you wanted to think about Lagrangian?
Oh, okay. So firstly, the initial version of this didn't have this notion of fair value and didn't have the bottom term in it. And and in certain markets like you know, in crypto markets, I don't know what the notion of fair value would look like.
Right.
So, but
my second question
yeah,
was
yeah, but there are other markets where it kind of does make sense. Like if there are different kinds of grain, for example, in the ancient Egypt example, then maybe if they got, you know, fair value means that they've got comparable caloric content or something. And people like to think that for stocks, there's some notion of fair value as well. Yeah, but sorry, go on.
Can I go for one more? A quick one. It's just that, you see, I wanted to know what you think about the cryptocurrencies. So independent of this modeling, I mean, what does the modeling?
Oh, okay. Yes.
I always want to ask kind of difficult questions because you know that they saw this thing about them being completely Ponzi schemes and schemas and stuff, right? And I was kind of wondering, I mean, you're treating them as something that's vaguely sensible, right? Because they are fitting. It's your third example of this setup.
Oh, okay. So I don't want to imply that. So for the purposes of this presentation, crypto markets are examples of markets where people trade things for each other. And whether they're useful or not, this work says absolutely nothing about that.
Okay.
So and I guess my general view is that there's different mechanisms that people have evolved at various times for how do you formalize the notion that people who don't know each other should trust each other. And so fiat money that is backed by the state is one way of formalizing that, and cryptocurrency that people are prepared to rely on because of, say, proof of work or proof of stake or something, and because of encryption, is another way of kind of formalizing trust between strangers. But how kind of persistent exchange value comes into that is really a bit of a mystery. And there's a long history of exchange value kind of suddenly evaporating for fiat currencies. So so the answer is I really don't know. I have to say the whole all the developments that we've seen in the past few years actually completely failed to predict. So I'm not the right person to ask about that stuff at all.
The reason I was asking is because we've been asked to be part of a cryptocurrency sort of project, which did not go anywhere. Kind of, you know, thank goodness we didn't kind of have any. We didn't have to think hard about it.
Yeah. Well, that's interesting. I mean, I mean, the whole thing's very interesting. That's for sure. And I think that I don't know what the nature of the project is, but I think
Or was actually.
yeah, is that regardless of what you think the function of cryptocurrency is going to be in 5 years' time or in 10 years' time, there's a tremendous amount you can learn today from people's kind of social interactions and the nature of trust and so on by studying crypto markets. And you learn a lot of extra stuff from them because they're new and because they're different from a lot of existing financial markets.
Yeah, that's good. That is kind of very reasonable, I suppose. That, yeah. And it's also very reasonable, this idea that in the world we live now, it is very important, this business of knowing what can happen when you have to trust people that you don't know, right? Because that's a hard one.
Yeah.
Too. Thank you.
So I have a big thought about maybe one possible direction. So not knowing much about finance, it occurred to me that like this kind of model seems a bit analogous to like a chemical reaction network where instead of some class of equities that people trade, you have chemicals of different species. And instead of having these transactions, you have chemical reactions that can happen at different rates. You imagine that all happening stochastically. And the reason I bring this up is that I have not studied that stuff in great detail, but a lot of people have worked hard to figure out ways to simulate systems like that stochastically, and I thought maybe it could be a good set of literature to look at for ideas about how to, say, do the sampling in a more efficient way or figure out these.
Yeah.
I don't know if you've looked into stuff like that.
No, I mean, I think that's a really good suggestion. And there is in the kind of the chemistry literature and the quantum physics literature and so on. I mean, there's people have done a ton of, they have equally hard simulation problems and have done a ton of work. So I think that probably is a good place to look.
But one thing that I don't see an analogy between is like this notion of arbitrage, right? And that's a big part of the story you're telling, and that I don't see how that translates over.
Yeah. So, yeah.
That's because I don't understand what arbitrage is in general. It's one comment.
I had a couple questions. One was, one was just a question of whether it makes any sense at all, which was to find the degenerate, like to stay off the degenerate weights problem. I was wondering if it made any sense at all to have the samples that kind of keep track of, have internal state in a kind of deep learning way, where they try to where they get rewarded for being in the right regime.
Oh, yeah. No, so I think that's a really, yes. So like a much more intelligent kind of important sampling. And you could learn, you could
learn their own, where the arbitrage, where it is or something.
Yeah, so I mean, I think that's kind of promising, but you still have to start. Like if you start in the wrong place, then you don't have a hope. So that's a big problem. Is that you kind of have to start like somewhere reasonably close to the typical set, because otherwise you're just wandering around in space and there's kind of nothing to learn because you're not close enough to anywhere where you could learn anything.
Okay, gotcha. And the other question was just you were talking about portfolios, and I'm guessing that you had the vague intuition that maybe monoidal categories could,
So
I'm wondering if that is obviously wrong for some reason.
Yeah, so there was a big problem of interpretation there. So what you want is to model kind of bundles of assets with tensor products of objects. That would be a really nice thing to do. But then what do the arrows actually mean? Because and it starts to get kind of complicated enough when the seminar is in 2 days' time, so that it seems better to just to put the question off. Yeah.
I mean, you could say I'm trading this whole portfolio for this one. And the rule is that if I can trade A for A prime and B for B prime, then an automatic way of trading A plus B for A prime plus B prime.
Yeah, and so you get like a lot of complicated arrows between two portfolios because if there's different ways of
Okay, so it's not obviously wrong, but it's also not very super obvious how to do it.
I think it just would take
the
some
simulation
patient
is
work.
terrible.
Yeah. But it would be really nice to get that to work, though. I mean, that's okay.
I have a brief question, which is just simply, so it sounds like you can simulate these toy category examples, but we want to get to the larger categories to do something interesting. How many assets is the smallest interesting example?
Oh, you know, I think actually not very many.
Okay.
So, I mean, real markets are interesting once they have dozens of assets. But I think you can learn interesting if you could like have you know, half a dozen or a dozen assets and some interesting structure between them, then I think you can already learn some interesting things. I mean, there's for example, I don't want to come back to, well, let's say if you only model the G10 currencies, or if you only model the half dozen most popular cryptocurrencies, or if you only model kind of barley and wheat and sorghum or whatever, then I think there's still interesting things you could learn.
That's more in reach than I was thinking.
Well, I have a question about sort of correctedness. I don't know how to phrase this. So the kind of exchanges in your markets are directed, right? Like an arrow. In some sense, I mean, if there's an arrow from silver to wheat, this is supposed to mean that there's somebody who will exchange, you know, a piece of silver for a sack of wheat, or some rate. But then, so suppose like if I go to market and there's some guy who's selling wheat, you know, one sack of wheat per piece of silver, and some guy who's selling wheat at 2 sacks of wheat for a piece of silver, then like the way that I arbitrage this is that I, you know, buy 2 sacks of wheat from the guy with the good price, and then I, you know, exchange one of them for a piece of silver with the other guy, and now I have, you know, a free sack of wheat. But this only works if the arrows are in some sense going in both directions. So if there's just 2 guys selling wheat at different prices, but none of them will like buy wheat, if there's nobody who will buy wheat, then you can't really do any kind of arbitrage. Like it's still, you know, obviously, eventually everybody will only, like nobody will buy from the person with the red prices unless they lower their prices. So, but it doesn't actually like have to kind of equilibrate unless you can also pass the other direction.
So okay, that's a really good point. And this is in that sense, it's kind of a sloppy use of the word arbitrage, because normally what people mean by arbitrage is the thing that happens around loops,
right?
Like you said. And this argument that parallel pairs shouldn't have, quote, arbitrage because that kind of gets competed away. That's sort of a more subtle argument, though I think it's still true for the reason that you said. But you should probably call it something else, and you should, and maybe you should have a different constant term in front of that term of the Lagrangian. So so I think that's a really good point. In practice, there's lots of markets which are effectively the arrows are directed, and there just isn't an arrow in the other direction. Like there are many, like if I have some funky bond, then I can offer that to a dealer because I own it, but a dealer is not going to offer. It's not going to offer that to me because I'm the one who owns it, not them.
Right.
And it happens a lot in barter markets as well. So I think that the directedness is typical, even though that kind of is hidden away in the way that we normally think of centralized markets. All right. Well, thank you so much for your patience, and it's great to meet you all.